Let us now discuss one of the important equations used in the electromagnetic field theory called as the equation of continuity. For this, first let us take a DC circuit, like a circuit having a power supply and a resistor. So if we take such a DC circuit, the divergence of the current density vector is equal to 0 at some point in that circuit. So this is true according to the Kirchhoff's current law. Whatever the inflow of current is equal to the outflow of current. We can write here J bar as the charge density into the velocity vector. So you can write like this. And this divergence of J bar equal to 0 is also true according to the Ampere's law. So in Ampere's law, if we take the divergence applied on the both sides of the Ampere's law equation, then remembering that the divergence of curl is 0, we will also get therefore divergence of J bar is equal to 0. So for DC circuits, Ampere's law is valid there. Now let us consider the AC circuits. So in AC circuit, we have considered here a power supply, a oscillator and a capacitor component. So there is a flow of current, say I. Now in the capacitor, I consider an imaginary closed surface around one of the plates. Now if we take such one of the plates, there is a flow of current which is going outside. So there is no inflow of current, there is outflow of current. Therefore I can write the current I is equal to negative rate of change of the charge stored on that plate. So minus dou Q by dou T. Now let us rewrite this equation by considering I, the current I, as the closed surface integral of J bar dot ds bar. So that is, I take the closed surface integral over this imaginary surface which is enclosing this plate. So I can write like this, and the charge Q which is stored in that plate can also be written as the volume integral of rho dV. So now therefore the equation 1 can be rewritten like this: closed surface integral of J bar dot ds bar is equal to minus dou by dou T of rho dV. So here we have one side the surface integral, on the other side the volume integral. So let us rewrite both in the same integral. So this can be done using the Gauss divergence theorem. So using Gauss divergence theorem, I can write this closed surface integral of J bar dot ds bar as the volume integral of divergence of J bar dV. So therefore the equation 2 can be written again like this. So in place of this closed surface integral, I can now write the volume integral. So volume integral of divergence of J bar dV is equal to the volume integral of, that is, I take the derivative inside the integral. So volume integral of minus dou rho by dou T dV. So now we have both sides the volume integral. Therefore we can equate the integrand. That means we get the divergence of J bar is equal to minus dou rho by dou T. So this is the equation now for the AC circuit. So thus we see that in the DC circuit, even though the divergence of J bar we got it as 0, but it is not always true. If you take AC circuits, the divergence of J bar is not 0, but it is given by minus dou rho by dou T. So this is called as the equation of continuity. And also we see here that the Ampere's law, according to Ampere's law, the divergence of J bar is equal to 0, and it is true in DC circuits, but Ampere's law will not be true for the AC circuit, because here divergence of J bar is not equal to 0. So this implies that the Ampere's law is also not a general equation. It is also needs some correction. It's not a perfect equation. We have to make some correction in the Ampere's law, and that is done by Maxwell, called as the modified Maxwell-Ampere law, which we will discuss in the next section.